In this video, we're going to look at inequalities. We've looked at equations in the past. An example might be 2x is equal to 8, and we would solve and we would say x is equal to 4. This is a statement of equality. It's saying that this number x is equal to 4. With inequalities, we can have them equal to, greater than, or less than. So we'll be given a number or numbers, and we'll be looking to find now the values that satisfy that inequality. Let's start off with some basic notation. If I said x, which is just a number, is going to be greater than 1, and we would use the notation here, we can pick all numbers bigger than 1. We can't include 1, so we could choose 2, 3, 4, 5, 6, 7, 8, and so on and so forth. If we said that x was going to be less than 4, we could pick all numbers less than 4. So x could be 3, it could be 2, it could be negative 10. If we have x is equal to or greater than, we would use this sign. So if I had now x is equal to or greater than 5, we could include 5. 5, 6, 7, 8, 9, 10, a million, 10 million, and so on and so forth. If we have x is equal to or less than, we would use this sign, and for example, this might be negative 3. So we could have negative 3, negative 4, negative 10, negative 20, and so on and so forth. So this now is the difference. We have an inequality. So it's saying our number can be equal to, greater than, or less than a given quantity. So let's have a look at where we would see these in real life. Often when you go to the fairground, there'll be a child's ride, and we'll say that h is the height of the child. Sometimes there'll be a restriction. So we can say that the height of a child can be no more than 1.4 meters, h being the height. So this is what we would call a constraint, and we can use inequalities for constraints. So for example now, if I'm probably about 1 meter 80, I wouldn't satisfy this inequality. I'd have to be 1 meter 40 or less. Let's say we looked at something different and we went to the cinema and we wanted to watch an 18 movie. We could say now that the age would have to be at least 18. So we could say that A was equal to or greater than 18. So if I was 19, well, perhaps not, that would be perfectly fine. Yet if I put in here that I was 15, then that does not satisfy the inequality. 15 is not equal to or greater than 18. If we look at a sports club, we might have a senior category. So when we go to a sports club, we might have seniors. Let's put this on. Now a senior, and we can say now that the age of a senior will be equal to or greater than 21, yet in turn less than 40. Once we get to 40, we would be a veteran, for example. So we could put loads of ages in here. We could be 21, we could be 22, but we can see that this is a strict inequality here, that we'd have to be less than 40. So these are all examples of inequalities. We might see something more challenging in an inequality where we have what we call a constraint. So for example now, if I went to the shop, so I'll go to a shop and I take 50p with me. So I'm going to take 50p with me. Let's put 50 instead of £5, we'll do 50p. And the chews that I want are 8p each. Okay, so let's just write this down. So I take 50p in. So 50p will go in, and each chew is 8p. We could write an inequality for the number of chews that I could buy. If we let x be the number of chews, or we could have n, number of chews, I could write down this inequality. I could say that 8x, remember, x is the number of chews I can buy, must be equal to or less than 50. We could go ahead and simplify this, but it's just saying however many I buy. So if I bought 1, quite clearly 8 times by 1 is going to be 8. If I bought 2, that's going to give 16. There'll come a stage though if I choose 7 or pick up 7 shoes, that's 56. So this wouldn't satisfy the inequality. So that's a sort of a basic intro to inequalities. They're statements saying we can have equal to, greater than, or less than a given quantity. What we're going to do in the video is look at some typical questions that we might be asked and then go on and look at some graphing. Okay, so what we're going to do is list values that satisfy an inequality. When we say satisfy, which I've used a couple of times, it's just saying which numbers does this hold true for, which numbers can we use. So what we're going to do now is the following. We're going to list, and I'm going to write this down, 3 integers. So 3 whole numbers, an integer is a whole number, that satisfy the following inequalities. So let's say we've got now x is going to be greater than and strictly greater than 7, and I want to list 3 integers. Well, I could choose 8, I could choose 9, and I'm going to choose 21. I could of course chosen 10, but it just says now we can have anything that's bigger than 7. Let's go for another one. Let's say we've got now x is going to be equal to or less than 4. Well, I can choose 4, I can choose 3, and I can choose -1. So we're looking for numbers now that are going to be less than or equal to 4. Let's say I had now that x is going to be less than and strictly less than -9. We could have now -10, we could have -11 and -40. If we said now that x is going to be greater than or equal to or greater than, let's say, -6, then I'm going to have -6, -5 and 10. So that now is listing 3 integer values that satisfy inequalities. On one of these here, we looked at what we call a double inequality. So the age of the senior had to be at least 21, yet in turn less than 40. We might be asked to list all integers. So let's have a look at that. Let's list all integers. So all integers that satisfy the following inequalities. Sometimes you might have 3, we might have all of them to do. So what we're going to have then is x is going to be greater than and strictly greater than 1, yet in turn equal to or less than 5. So I want to list all of the integers that satisfy this inequality. 1 doesn't satisfy it because it has to be greater than 1. So we're going to have now 2, we're going to have 3, we're going to have 4, and we're going to have 5. We can include 5. So if this was a strict inequality, we couldn't. Let's look at another one. Let's say we have -2, and then we're going to include, so we can say that x will be equal to or greater than -2, yet in turn it's going to be less or equal to or less than, and we'll go for 3. So if we think of the numbers, -2, -1, 0, 1, 2, and we're going to have 3. So those now are all of the integers that satisfy these inequalities. If we had, for example, now something slightly more challenging, let's say we've got -10 and we've got now 2x. So 2x, and then we're going to have we'll go for -4. So with this one, I could divide right through the inequality by 2. In a later video, we will look at dividing and multiplying by negative numbers because we do have to change the inequality sign around. In the next video, when we're solving inequalities, we will look at that. So what I can do is divide each part now by 2. So that's giving me -5. We're going to have x, and then we're going to have -2. So we want to list all of the integers that satisfy this. We could have -4, -3, and then -2. So that gives us our list right there. Okay, so we've looked at integer quantities and we've looked at what satisfies them and what they kind of stand for. We can actually graph these on a number line. In another video, we'll look at shading regions on graphs, but for now, what we're going to do is look now at drawing these on a number line. When we go back to our notation, and I'll introduce it here, if we have now a strict inequality where we don't include it, we have an open dot. If we have this one, so this is going to be an open dot, it doesn't include it. If it does include it, we have a solid dot. So it's inclusive in this example now of 5. So all we're going to do is use this, put these on number lines and represent inequalities. So again, we'd have a solid dot just here. So we'll start by reading some and then we'll write some of our own and show them on a number line. Okay, so let's have a look at some examples. So this one right here, what we've got now, we've got the open dot at 1. We've got all values less than 1. So what we can say from this then is that x is going to be less than and strictly less than 1. If you want, you can look at the way the arrow's pointing. It's pointing that it's going to be bigger than x. And we can see from here, I've located 1 on the number line. It's an open dot, so it's not going to include 1, and it's a strict inequality. If we look at this one, we locate where we start, which is -1. We can see that it's inclusive, and it's going to be all values now where we have x is going to be equal to or greater than -1. So this time what we can say is that x will be equal to or greater than -1. Or if you like to write it the other way round, you can do it like so. I appreciate that this is probably more intuitive or easier to do as we've got the direction of the arrow. So looking at this, I'd probably actually write it the other way around. So you're starting now with x at the front. So if we look at the next one, we've got now x, we've located the -2, it's inclusive, so we can say now that x will be equal to or greater than -2. With this one, we have a double inequality. We can see that the two values we're going to have are going to be -2 and we're going to have 2. We're going to take x and we can see it includes both of these. So we can say that x is equal to or greater than -2, yet in turn equal to or less than +2. This one right here, we can say now that x is going to be strictly greater than -3. Just think about it now. Put a number in a box. Pick a number. Does it satisfy this inequality? So if I chose now, let's say 1, is 1 bigger than -3? Quite clearly it is, and we can see that that's located just here. Okay, let's do the next one. So we can see what we have are our values. And as you go on with your studies, you'll hear these being called critical values. We've got -2 and 2 again. This time we've got a strict inequality. So we can't include -2, but we can include +2. If we look at the next one, we've got now x is going to be greater and strictly greater than -1, yet in turn less than and strictly less than 3. So if we were asked to state all of the integer values that satisfy this inequality, this wouldn't, and it would be these ones just here. With this one, we could include that one, we could include this one, we could include this one, but not that one. So it'd be -1 to 2 inclusive. Okay, let's quickly finish these off. So this one right here, we've got now x is going to be strictly greater than -1, yet in turn equal to or less than 3. This one we're going to have x is going to be equal to or greater than -4, yet in turn strictly less than 1. And then finally we're going to have on here that x is going to be equal to or greater than -5, yet in turn strictly less than 10. So that's what we've got. So let's go ahead and do some for ourselves. Let's just do this and we'll just draw a basic number line. Often in exams you'll be given them. So let's go ahead and do this one. X is going to be equal to or greater than +5. So all I do here is just draw a little number line and I'd locate +5. So let's go ahead and do that and we could just show it. Like so. So let's do +5. So what I'll do, I'll put 0 just here. So 0 is going to be just here. We'll say that 5 is here. I'm then going to have a closed dot because it's inclusive, and I'm going to represent this by an arrow pointing to the right. We could of course continue it. My arrow was going to be pretty wonky if I did it, but it's all values now where x is going to be at least 5. That's another way of saying it. X is equal to or greater than 5, x is at least 5. So 5, 6, 7, 8, 9 and 10. On the same number line, I'm going to do that x is going to be less than and strictly less than negative 1. So what we'll do, we'll locate negative 1 just here. We'll put negative 1 here. This time I'm going to have an open dot, and we're looking at all values in this direction right here. So if we think now, is negative 2 less than negative 1? Yes, it is. So it would satisfy the inequality. If we look at another one, let's say we've got x is going to be, and we'll go for equal to or greater than 1, yet in turn strictly less than 7. So what I'm going to do is locate 1 just here. I'm going to locate 7 just here. And I'm going to have now the closed dot at 1. So closed dot at 1. I'm going to have the open dot at 7. And then we draw a line between the two. So that gives me the inequality here. Let's look at one more. Let's say we have now negative 2. We will be greater than negative 2, yet in turn now less than or equal to 0. I've located 0 here. We will have negative 2 just here. I appreciate the scale isn't great. And then I'll just represent this one. So we'll have an open dot. We will go to 0 and we'll have a closed dot. So that is drawing now an inequality or inequalities on number lines. Let's just finish off with a couple of wordy questions and look at writing some inequalities. So we're told Bob needs to buy seats for a garden party. He knows there will be more than 50 people there. Write an inequality for the number of seats he'll need to buy. Let n be the number of seats he needs. So they're going to be more than 50 people. So n is the number of seats. We can simply say that n must be greater and strictly greater than 50. So that's the inequality. Nice and straightforward. The number that he needs is going to be more than 50. This question could be slightly more challenging. For example, if we were told they cost, so let's change the situation, they cost £8 each, so each seat is going to be £8, and Bob has only saved, let's say he's got £3,167. So what we could do is look at writing an inequality for this constraint. So n is the number of seats, so 8n must be equal to or less than 3,167. So this is a different inequality and a constraint. So for example, he needs more than 50, yet in turn now he knows that 8n must be equal to or less than 3,167, as that's all he's got. So for example, if n was 1, if he bought one chair, that would be perfectly fine, so that would be £8. 2 would be 16, but there's going to come a point now when n is going to be a value such that we can't buy any more. And essentially we could work that out. That's what we're going to do in the next video. Okay, let's just do one more. A school can hire coaches with 53 seats on each. The school needs to transport 420 pupils on a trip. We're asked to write an inequality to represent this situation. So this one is slightly less structured. What we'll do is call x the number of coaches. So we could write let x be equal to the number of coaches. So number of coaches. If you're ever stuck, x or n is generally quite good. So what we can say then is the following. We can say that 53 lots of x must be equal to or greater than 420. So this tells me the number of coaches. Each coach can carry 53. So for example, if I had 1, that's not going to work because quite clearly we can't get 420 kids on 1. 2, 3, 4 and so on and so forth. We could look at all of the values that satisfy this inequality. So if we think about it reasonably, dividing 420 by, let's just do this, let's get the exact value. So if we do 420 divided by 53, so we're solving this in a very similar way now to an equation. isn't an equation, what we can say then is that x must now be equal to or greater than 7.92 dot 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 dot. So in context we can say x must be equal to 8. We can't hire now 7.92 coaches, as these are discrete values. Think you can have 1 coach, 2 coaches, 3 coaches, dot dot dot. We can't have now 7.92. So it's saying the number of coaches I need has got to be greater than this value essentially, so we'd have to have 8 coaches. And we could go ahead and work that out. If we do that, that's going to give us, what would that give us? 424. So 8 times by 53 is going to give us the 400. Let's just check I've done my maths. 424. So we'd have to get 8 to transport them all. If I took 7, then we'd have 53 less than this value, and we couldn't do it. So we could hire more, quite clearly. We would look at other constraints to deal with this, such as the cost, so what our budget was, but this just gives us an idea that the number we need is going to be at least 8. So this is the smallest number that satisfies that inequality. So something more challenging at the end, but hopefully that's given you a good introduction to inequalities in terms of a notation, in terms of listing integers, in terms of putting them on a number line and interpreting them.